This is a lesson on conservative forces and potential energy in the work and energy unit. When I first introduced forces, I talked about critical differences in the types of forces. And this is where there is a critical difference between types of forces, the difference between a conservative force and a non-conservative force. And all forces are either conservative or non-conservative. They may take on other qualities as well, but all forces can be divided into these two categories. For a conservative force, the work done, and notice that the definition of conservative is in relation to work. For a conservative force, the work done is not path dependent. It's not dependent on the path. So some examples of this. What I see is non-contact field forces, such as gravity and electric force, magnetic force. You'll see that when you get to them. These are field forces, and the work done isn't path dependent. So like if you think about moving an object from the top of the table to the floor, it doesn't matter if it moves over an angle or falls straight down. The gravitational field will do the same amount of work because of the displacement vector and the force vector for both situations are the same. You will end up with a path independent work. It's not dependent on the path. However it got there, the work is not dependent. The spring force happens to be like this. No matter how many times the spring goes back and forth, we only care about the initial position and the final position, not how many times it went back and forth in order to get to the final position. Additionally, non-conservative forces are work done that depends on the length of the path the force acts over. These are typically contact forces. You can imagine friction. The work done by friction depends on how long those two surfaces were in contact. An applied force, how long that applied force was actually applied to the object. The normal force, the tension, all of these are contact forces. And what we can do is we can conceptualize, instead of having just a single net work term, we can divide it up into work done by conservative forces and work done by non-conservative forces. Keep this principle in mind as we move to the next lesson. But I wanted to talk a little bit more about potential energies, because this idea of conservative forces, if their work is path independent, how can I not do that calculation where I take the path into account, right? Because the work done by a force is F(d) cosine theta. If I know d doesn't matter, how can I take that completely out of the picture? How can I not worry about the path it travels? Well, it turns out we can think about in terms of potential energy. And that's what potential energy is, and it's energy associated with a position. All right, I just think about where the object is in a field or attached to the spring, wherever its initial position is and its final position. So again, we're going back to the state function. Energy is a state function. There's an initial and a final, and we can think of initial potential energy and a final potential energy. The symbol for potential energy is formally known as U. Okay, so you have U gravity, U electric, U magnetic, U spring. These are all potential energies. Gravitational potential energy near the surface of the Earth, you can already guess there's a universal gravitational potential energy, which I have a lecture on too. But near the surface of a planet will be, and I call this PE for potential energy, and gravitational. The gravitational potential energy is mass times gravity times the height in the gravitational field. And that makes sense because this is an energy of position, where it is in a gravitational field. And notice that this vertical distance measured is with respect to an assigned coordinate system. Again, we're going back to assigned coordinate systems, and why I've been emphasizing them is if there's not a coordinate system assigned, you don't have a reference point, and you have no way to measure potential energy. So make sure that you're setting, where is y equal to 0? Where is gravitational potential energy equal to 0? And it may be obviously on the ground, right? But it could be that you're in a second story building and you mark that as 0. It's arbitrary where you marked 0, but you need to mark 0 from which to measure these heights. I put down here to note because I was talking about a change in potential energy. A change in potential energy comes from a change in height. And remember, a change is always final minus initial. So watch out for changes in height, and that will give you a change in potential energy. I'm going to do a lecture that relates the work done by the gravitational potential energy and this property that it's the negative change in potential energy. That's going to be a useful identity for us to develop our ideas for conservation of energy, but that these two are negative values of each other. They're the same like absolute value, but they're negatives of each other. Whatever work done is by gravity is negative the change in potential energy. So let me give you an example here, and I'll set y equals 0 down here. And let's say that we move an object up in a gravitational field. So y initial is 0, y final equals some value I'll call h. Okay? So when I think about this, I see that it has a positive change in the potential energy, right? It moved up in the gravitational field. It gained gravitational potential energy. So it has a positive change in gravitational energy. It gained it, right? When we look at the work done by the gravitational force, if I think about a free body diagram of whatever object I have, the gravitational force is downward and my displacement vector is upward. So when you look at the sign of the work done by gravity, it will be a negative value, right? It will be negative. Gravity's down, displacement's up. I have a cosine 180, and that will give me a negative value. So we get this relationship. We'll keep this in mind as we move forward to the next lesson. But I wanted to just introduce, like, how do I use potential energy in a problem? And so I have this information up here. Throwing a rock off a bridge. The rock is thrown off the bridge to 20 meters below. So off the bridge, 20 meters below. And there's an initial speed. And I'm a little uncomfortable because they really didn't give the initial speed. They didn't say if they threw the rock up, if they threw it at an angle, if they threw it straight downward. I don't know what's going on. What I will do is I will draw a bridge, and then I will draw the water below, and I can make note that here's the 20 meters, right? I'll set 0, y equals 0 down here. We'll say y final equals 0. We have y initial equals 20. And the rock goes down, hits the water below. And like I said, I don't know if it's thrown up. I don't know if it's just thrown straight. I don't know if it's thrown downward. I don't know. And actually, see, it says that the speed should be independent of the direction thrown. We'll see this. Calculate the work done on the rock by gravity. Okay, work done on the rock by gravity. Well, I know the gravitational force. I don't know initial speed, or I know initial speed, but I don't know final speed, so I can't really find the work that way. But I know the work done by the gravitational force. I can figure that out. I know the mass, I know gravity, and I can write this equation out for A. The work done by gravity equals the gravitational force, which is mg, times the distance that it covers, d, and then cosine of the angle between them. Well, the displacement vector is downward. We'll see that. Displacement vector is downward. The weight force, the force from gravity, is also downward, so I get a cosine 0 degrees here. I'm going to plug in what I know. 0.5 for the mass, 9.8 for gravity. The distance is 20, and cosine 0 is 1. And when I plug all of this through the calculator, I get a positive value. I expect that gravity is causing the rock to speed up. So it's going to be adding energy to the system. I get a positive sign here. And you can see half of 20 is 10 times 9.8. I get 98 joules. And we're going to note that this is positive. We expect it to be positive. It's causing it to speed up. Part B says calculate the change in potential energy due to gravity. Okay, so the change in the potential energy due to gravity is going to be the mg times delta H. Well, I still have half a kilogram rock. I still have 9.8. If I do H, delta H is H final minus H initial. H final is 0. H initial is 20. So I'm going to do 0 minus 20. Always final minus initial. Final minus initial. Well, I get the same numbers as up here, but a negative sign, and I think I expected that, right? We know the work done by a conservative force is negative the potential energy of that. So we get a negative here. And does that make sense? Yes, we are losing potential energy. The rock starts with a lot of potential energy. It's high above the ground. It has a lot of potential energy to begin with. The gravitational field has a lot of potential to do work on that rock when it's that high above the ground. When it falls down, it loses potential energy, and thus we're getting a negative sign. It says assuming negligible air resistance, so we don't have to worry about any other forces, basically. Use the concepts of work and energy to show that the rock strikes the water with a speed independent of the direction thrown. Okay, this is interesting. How do we do this? Well, I want to find the final speed. They give me the value, but they're saying prove it. Show that. We're going to prove it. So we're going to assume we don't know the final speed. We know the initial speed, right? V initial is 15 meters per second. And we don't know the angle. We don't care the angle. And they're saying prove that you don't. So what I'm going to do is write out what we know about work net. The change in the kinetic energy. Well, the final speed is in that kinetic energy term, right? And the only force acting on the rock while it's falling is gravity, and we have the work done by gravity. So I know that the work done by gravity, which is the work net, right? These two are the same thing, has to equal the change in the kinetic energy, which is 1/2 mv final squared minus v initial squared. So if I solve this equation for V final, that would let me solve for it. V final, I'll put squared here, equals. Well, it looks like 2 times the work of gravity divided by m plus V initial squared when you do algebra on this. You can pause it if you need to check my algebra, but that's what it is. I'm going to go like this. V final is the square root of V final squared, which is the square root of all this stuff. And I can plug it in. 2 times 98 divided by the mass, which is 0.5. Add on 15 squared, and then when I get done with all that calculation, I'll square root it. And the final speed, imagine that when you run all this through your calculator, you get 24.8 meters per second. And you may be uncomfortable with this. When we did projectile motion, when we were throwing things and letting them off the bridge and hit the water, etc., we cared about the angle. We cared about it. But what we're seeing with a conservative force, this is a conservative force, right? It's path independent. It doesn't matter if it goes up and comes back down. It doesn't matter if it was thrown straight down. All it matters is that distance in that conservative field. That's all. The H initial, H final. Could have went up and come back down. We don't care. Initial state, final state, done. We don't care what happens in between. And that's the beauty of conservative forces, is we can just take the initial and final into account. We don't care about that angle. So this should make your calculations easier than what you saw with working with vectors. This is a scalar. We don't have to work with components with scalars. It just is.